So now let's look at other photon-based lithography. So first topic is interference lithography. I'm sure you have heard about interference. So here, for example, so we have the water wave. So we have the water wave. So this water wave and this water wave, they will meet and they will interfere. So as you can see, at one moment, so this part is the peak, this is the peak, and this is the valley. This is the peak, this is the valley. You can imagine if this is the light, so we also have the similar light intensity profile. So this light can expose the photoresist. So this is the idea of the interference lithography. So at this moment, this is the peak, this is the valley. Then you can tell where, if this is the photoresist, so which area that will be high exposure dose. So you know this part is high exposure dose. So how about here? In this area, high dose or low dose? So you may think this part should be low exposure, this is high exposure. So actually, this part is also high exposure dose because half period later on, because half period later on, so this part will become, the valley part will become the peak will become the valley will become the peak. So this is the area with the exposure. So the area in between the valley, between the peak and the valley is the area that has no exposure. Okay. So here is the summary overview of the interference lithography. So as we know that, so when we have the two beams of the light, two light beams, they will meet and they will interfere. The pitch is given by lambda over 2 sine theta. So first, you can see it's very simple and fast. We do not need a photomask or lenses. So all we need the two light beams to meet at the wafer surface. But the limit is that the only thing we can create is the periodic structure. So we cannot make arbitrary patterns. And we need high spatial and temporal coherence of the light source. So we will see what is the coherence later on. And also we will see later on that actually we can do something to relax requirement for the spatial and temporal coherence. For the application side, so here I talk about application for the optics. There is also application for other things. For example, the biosensors. They make periodic structures can be used to make the biochip or biosensors. So here I want to talk about maybe one example. So for the subwavelength optical element, so we will talk some of those things when we in the chapter nano-imprinted lithography. So here I talk about distributed Bragg reflector lasers. So we know that. So normally we need a mirror. So we need a mirror to for the light reflection. But when we have a waveguide or when we have a laser, on the wafer, it's not convenient to put the mirror on the side. So we cannot put the mirror because the mirror is a bulky devices. So we cannot put the mirror on the side. So what we can do? So we can make some gratings. We can pattern some gratings on top of the fiber or waveguide. So when we pattern the gratings, the light can also be reflected. So how come? So you can imagine the light coming in. So when it can feel the lines on the wafer on the surface of the waveguide because of the evanescent wave. So there will be some reflection come back. Then keep going here. There will be more reflection at the second one, and more reflection. There is also some reflection on the third line. So you can see they go back like this from here all the way. So the requirement is that when the reflected light, they are in phase, then they will interfere constructively. So you have the reflection. So we have many grating lines. So in the end you get very high reflection. So it's called distributed, because for the mirror, if we have the mirror, so all the light is bounced back from the mirror. But here, the light is bounced back from across the grating depths, across the grating areas. So it's not at the same, it is not bounced back at a single spot, it is bounced back at so many different spots. That's why it is called distributed. So what's the requirement for the grating pitch? How far this should be? So you can imagine the distance here should be lambda divided by 2. So when they are lambda divided by 2, then all the reflected light, they will interfere constructively, so we get high reflection. But if there is the index, if we have the index here, the reflex index of the material is n. Then this should be lambda over n. So lambda over n divided by 2. So we can calculate the light intensity profile on the photoresist surface, so which is given by this equation. Now, this equation looks like complicated, but actually it is not so hard to derive this equation. And I will later on upload the derivation of this equation. So here is the light intensity on the wafer surface. You can see here. So the pitch of the grating on the wafer surface is given by, you can find out from this term. So 2 kx sine theta equal to 2 pi. So when 2kx sine theta, 2kx sine theta equal to 2 pi, then the x equal to the grating pitch, right? The period of the grating. Actually, it is the period of the pitch of the grating. So then we need to know what is the k. So k is the wave vector of the beam, which is given by 2 pi. Normally it's 2 pi over lambda. So this is the k. For the case of the medium, the lambda become lambda over n. So in the end, you get 2 pi n over lambda, as you see here, 2 pi n, 2 pi over lambda. So this is the k. If you put the k here, you find out x. X is the period, which is given by lambda over 2n sine theta. So you can see the minimum pitch that you can get is lambda over 2. This corresponds to the situation of theta equal to 90 degrees. That means so one light come to the right, another light come to the left. They will meet on the wafer surface and it form the uniform pattern with the pitch lambda over 2. So this is for the case of the electrical field component of the light wave is in plane. So that means the field, the E, is perpendicular to the screen. It's perpendicular. Normally draw this way. The electrical field is perpendicular to the screen. So you have this formula. So when the E field is out of plane, so when the electrical field component of the light wave is out of plane, that means so the E field here is like this, the other one is like this. This is out of plane. So we have this extra term here, a cosine 2 theta. So as you can see, when theta equal to 45 degrees, when theta equal to 45 degrees, so this term become cosine 90 degrees, so it's 0. There will be no interference pattern. So this makes sense because when theta equal to 45 degrees, that means it's something like this. So this one is parallel to this one. You can see, so this E field and this E field, so they are perpendicular. So they are perpendicular to each other. You know, when two vectors are perpendicular to each other, they will not interfere. We also call them orthogonal. They are orthogonal to each other. So here is the example of the grating pattern that can be fabricated using interference lithography. This one is a 200 nanometer pitch by 2-beam interference lithography. So this can be done using the, I think it used 308 nanometer wavelength, which is the 308 nanometer wavelength. This corresponds to the, but this 308 nanometer come from excimer laser xenon chloride. So this one. This excimer laser gives you a 308 nanometer pitch. But this can be done using 4-beam interference lithography. So we have 2 beam. So we have one beam come from here, another one come from here. So we have 4 beams interfere on the wafer surface. You can get whole array, 2D whole array. Another way to do this is to do two exposures at orthogonal directions. That means the first you expose along this direction, then you rotate the wafer by 90 degrees, you expose along the other direction. Then you do the development, you can also get the same pattern. This is two exposure along orthogonal directions. So we know that the light intensity profile is given by this one. So the light intensity profile is given by this one. Then the dose exposure dose will also be sinusoidal. It will be sinusoidal, this term, sinusoidal term. You can see here. So the dose is given by this sinusoidal term. So it is like a kind of a gray scale lithography. So here I call it gray scale because the light intensity is not binary. The binary means the light, something like this. Then another one. So this is the binary. We call this one as the binary light intensity. So this one is not like this. It is a gray scale. But this does not mean we get a curved resist surface. So this depends on the contrast of the resist. So this depends on the contrast of the resist. So for the low contrast resist, if the contrast is very low, so then the pattern on the resist will be, the pattern could be something like this. So this is the low contrast. For the high contrast, it will be something like this. You can get some pattern like this. We have high contrast. So here for the positive resist, this is underexposed, you get something like this. Overexposed, this is 20% duty cycle, 50% duty cycle. So here is, if there are high contrast, means there is this threshold intensity. So this is ideal resist. For ideal resist, we just have the contrast is infinity. You get the threshold. So you get the vertical. The profile will be something like this. High contrast. For low contrast, as I said, you get something like this. So how to do the interference lithography? So normally people think we need the two beams. So we need the two beams. We can have two lasers. But if we use two lasers, you can see again. Oh. Two lasers. Can you do the interference lithography using two lasers? So in principle you can, but in reality this will not work. This will not work out. Because if we look at here, if we have one laser, one source here and another source here, if they are not correlated, so that means those two persons, they do things randomly, then you cannot have stable interference pattern. So the same thing is for the lasers. So all the lasers, even the best lasers, they are pulsed. So all the lasers, they are pulsed. So sometimes the pulse can be longer, other times the pulse is shorter, but all the lasers, they are pulsed. So if the lasers are pulsed, then they are not coherent, so you cannot use two lasers. So we have to use only one laser beam. So when we have only one laser beam, we can make sure that it will interfere well with itself. So one laser beam, here we have the beam splitter to split the beam into two branches. This branch comes from here and come here, go to the wafer. The other branch comes from here to here, goes to the wafer. So here we have the variable attenuator. But there will be some scattered light. So there are also scattered light from the red side. So those two scattered light will be compared at this chip. Then the phase error difference can be sent to this Prockel cell. So this Prockel cell can change the index of the material when you apply a voltage. So this way, so the error between the two branches can be compensated. So this is called the feedback. So this feedback can correct the phase error. So where comes the phase error? This phase error comes from a vibration. So we know that even a tiny vibration can cause a big phase change, because what we need the vibration to be smaller than lambda over 2. The noise should be smaller than lambda over 2. Otherwise, the pattern will not be, you will not form a periodic pattern. because they will average out. So actually, my colleague at the Princeton University, they have done in-field lithography in around year 2000. So they use the similar setup. So they use similar setup, but they do not use this feedback part. They just have two branches, no feedback, no particle cell and no feedback. So they always do the in-field lithography at midnight, because only at the midnight there is no car, no buses, no trucks on the road. There is the least noise, least vibration. Then you can get good exposure. Otherwise, if you do it during the day, the pattern will not be good. So this one we call it amplitude split. So here, at this beam splitter, the light amplitude is split to the left and to the right. It's called amplitude split. Another way to do this is called a wavefront split. So in this case, the top half of the beam will interfere with the bottom half. So the top half missed the mirror and got bounced back, will interfere with the bottom half and resist the surface. Here the resist the surface. So this setup is called a layout mirror. So the advantage for this one is, first, easy to tune the pitch. When you do the rotation, when you rotate the setup, you get different pitches. So on the contrary, for this setup, it's very difficult to tune the pitch because you need to move everything. If you change the angle here, you need to move the mirrors, the beam splitter, and the wafer, everything. But normally, it takes many hours. Take many hours to do the optical alignment and to change the pitch, the grating period. But for this one, you do the rotation, you can change the pitch. Second advantage, there is only one optical branch. All the light comes here. It is more tolerant to the environmental perturbations. This is the noise of vibration. It is more tolerant to noise of vibration because everything, if you have the vibration, if there is vibration, everything will vibrate at the same time. So then it will be less of a problem. There may be some defect. If there is some dust particle on the mirror, there will be some defect. There is another limit. So somehow we have this setup. The area here, the wafer side is normally less than 2 inches. You can have grating pattern over 2 inches. But we have this setup, the wafer here can be bigger, 4 inches, or even higher, even more than 4 inches. But this one is only 2 inch wafer size. So normally for research, this 2 inches is good enough. That's why people use this setup. There is no in-field lithography at the University of Waterloo, but there is one in-field lithography setup at the McMaster University in Hamilton. But this one is normally people do not buy the equipment, so they buy the part, they buy the laser beam, they buy the mirrors, then they set up the in-field lithography by themselves. So this is similar idea. So you have two mirrors. So the light come here, reflects it, come here, reflects it, come here. The same idea, you get the pattern on the resist. So we have mentioned that, so for the in-field lithography, we need the light to be, there is temporal or spatial coherence. So now let's look at what is coherence. So here coherence means correlated, related, not random to each other. For example, we know for the electromagnetic wave, the electrical field given by this general form for the plane wave. For the ideal plane wave, this phi, the phase should be a constant. But in reality, this phi is not a constant. It depends on the location, position, and also depends on the time. Depend on the position, depend on the time. So when this one is not a constant, then there is the coherent issue. So there are two types of coherence. So one is the spatial coherence, the other one is the temporal coherence. For the case of the spatial coherence, so we can imagine, so we have the light beam coming from the left to the right. This is the beam center. This is A point, A prime, and A prime prime. So you can imagine, when the A prime is very close to A, when A prime is close to A, so the phase difference, so the delta phi is much smaller than 2 pi, then we can see that the light beam of A prime and A, they will interfere. They will interfere and give periodic interference pattern. But for the case of A prime prime, the phase difference may no longer be negligible. Then the light from here and the soft beam from here, they will interfere, but the interference pattern will be unpredictable. We cannot have periodic patterns in the end. So this is the spatial coherence. So the spatial coherence says that we need to take the beam only the central part of the beam. So only that part of the beam is good. Those beam which should be blocked is not good. So this is you can see here. So what we do? So we use the lens. Then we have a pinhole, very small hole. So only the central part. So only the central part of the light passes through. The light outside is blocked. This is to gain the spatial coherence. Spatial coherence. The second one is the temporal coherence. Temporal coherence. So as we mentioned, so all the light they are pulsed. There is no ideal light source. So all the light they are pulsed light. So when you have the pulse light, you can imagine this pulse 1 and pulse 2, they will not be coherent to each other. That means they will be irrelevant. They will be irrelevant to each other. So the phase for the pulse 1 and pulse 2, they will be irrelevant to each other. For this particular case, you can see it looks like the phi for the pulse 1 and the phi for the pulse 2, they're differed by maybe pi. They're differed by pi. But normally, this should be a random number. So as a result, so we cannot interfere between pulse 1 and pulse 2. So we should interfere among pulse 2 or within pulse 1. Pulse 1. But that means the optical path difference, optical path difference, L2 minus L1 should be smaller than LC. If we look at here, so we have one optical path from here, come to here, and come to here. But this is L1. The other one is from here to here, and come here. This is L2. The difference between the two branches should be smaller than the pulse length. Smaller than LC. If we derive it by the speed of the light, then this becomes the time difference. So arrival time difference between the two branches. The arrival time between the two branches should be smaller than LC over C. That's why this is the arrival time. That's why it is called a temporal coherence. So now you can think about under what situation, under what length, under what situation we do not need to worry about the temporal coherence. So the situation should be LC over C. If this time LC over C is comparable to the exposure time, that means if this is equal to, for example, 1 minute. 1 minute. So if LC over C, the pulse duration is equal to 1 minute, and if the exposure time is within 1 minute, then this pulse and this pulse, they will interfere well. They will form the periodic pattern on the wafer surface. But what does this 1 minute mean? So normally for the best lasers, we have the best laser called the fiber laser. For the best fiber lasers, this LC can be 100 kilometer. It looks like very long. So this LC is 100 kilometer. But if this 100 kilometer divided by the speed of the light, it gives only 0.33 milliseconds. You can see, so it's only 0.33 milliseconds. So the pulse duration is only 0.33 milliseconds, much shorter than the exposure time. That's why we need to worry about the pulse length when we do the interference lithography. So now let's look at one example of the effect of the coherent limit. So in this case, so we have the light come here, So we have this is the mirror, and here is the wafer. So first, it is amplitude split or it is wavefront split. So you can see it's similar to this one. So it is a wavefront split. So if you rotate this one, rotate it, you get it something like this. This is the mirror, this is the wafer. Here the same thing. This is the mirror, this is the wafer. So this is the wavefront split. For this case, the coherent radius is given by 0.5 millimeter. So this is the spatial coherence. For the temporal coherence, the LC, the pulse length, is given by 469 micrometer. So now we want to know within which area, within which X area, we get well-defined periodic pattern. So first, let's look at the effects of the spatial coherence. For the spatial coherence, the requirement is that the d, the width, the diameter should be smaller than 2 times RC. So now we need to relate this d with x. So this d equal to this one, right? Equal to this one. So this one equal to b times sine 2 theta. So b sine 2 theta. So b equal to x divided by sine theta. So in the end, you get a formula like this. X should be smaller than this one. Smaller than RC over cosine theta. So here we need to know what is the sine 2 theta. So if you remember the sine 2 theta, so what is equal to sine 2 theta? Sine 2 theta equal to 2 times sine theta cosine theta. Cosine theta. Sine 2 theta equal to 2 times sine theta cosine theta. This is sine 2 theta. So this is the spatial coherence. For the temporal coherence, so we need the optical part difference. This is optical part here and another optical part here. The difference should be smaller than 469 micrometer. So you can see that when the light comes to this spot, when they come to here, they are the same. So the difference is that this one goes this extra distance, this one goes this extra distance. So we need b minus a should be smaller than LC. So in the end, we get something x should be smaller than LC over 2 sine theta. So how to get this one? So we know b. So b equal to x divided by sine theta. So the a, we need to find out what is a. This is a. So a equal to b cosine 2 theta. b times cosine 2 theta. So we know, if we remember, the cosine 2 theta equal to 1 minus 2 sine theta squared, right? So cosine 2 theta equal to 1 minus 2 sine theta squared. So this way, in the end, you get something like this. So this one should be smaller, or less than this one. So this is the requirement by the spatial coherence and temporal coherence. So what do we need? So we need the x value smaller than both. If we say this is x1, this is x1, this is x2. So what do we need? So this x value should be smaller than x1 and also smaller than x2. So this is the correspond to the temporal coherence x2. This green color is the spatial coherence x1. So with the good area, x should be smaller than both. That means only this area. So this area here. So the x value should be smaller than this value. Come from here, then come to this one. This is x value that you have good, well-defined periodic pattern. So what does this mean? What does this well-defined periodic pattern means? For example, if we look at this setup, so first, which spot give you the best defined periodic pattern? So this part you can imagine. So this part right at the corner, you get the best defined periodic pattern because first it is at the beam center. Secondly, the light, the light comes from here. then bounce back, then the other branch comes from here to come here. Sorry. Come from here to here. So you can see this branch and this branch, they have very little difference, very little. B minus 8 is very, very small. So this area has the best defined periodic pattern. So farther away, the pattern become worse. So if you draw it, it will be something like this. So this area is like this. You draw this. The pattern will be, you can see something like this. So this corresponds. This well-defined periodic pattern is come to here. The far away it corresponds to here. But in reality, the drawing, there should be many of them. It should be something like this. Maybe you draw them, there are many of the waves because the period is much smaller. So the period, you can see here, so the period is a few hundred nanometers. But the x value here is a few millimeters. So there will be many of the lines, then they decay. So far we have seen that. So we need coherent light. So is there any way to overcome this coherent limit? And this is actually can be done by using something called a phase grating. So we need this to have higher resolution. For have higher resolution, we need a smaller wavelength. But when we have smaller wavelengths, there is no good coherent light source. So we need to use phase grating to do the in-field lithography to relax requirement for the coherence. So how will this work? So here you have the grating, you have the light come onto the grating, then there will be diffraction. So the light will, this part is diffract this way, this diffract this way, and they will meet. So here you can see the light, the L1 and L2, they are always the same. But actually, if you think carefully, they are not exactly the same. It will be something like this. For any spot here, the phase, the any spot here, it will be, say, L2 minus L1. If this is the center part, if this is the correspond to the beam, if this one is L1, if this is L1, this is L2. The center of the wafer. Any spot here, it will be L2 minus L1 plus 2n pi. We have extra term. They are not always the same, but the difference between the different spots is always 2n pi. This term, this term is the integer number of the wavelength. This term can be ignored. So effectively, we can say that every spot on the wafer, the two branches, they have the same optical path because they are differed by the 2n pi. So now let's look at how to calculate this angle. So this angle is calculated by the grating equation. You can see it here. So when the light passes through a grating, there will be diffraction. So the light will go to all the directions. The light will go to maybe some other light come here. Each of the slit, the light goes to all the directions. So then we want to know what direction we have the maximum light. So this can be calculated based on this kind of drawing. So you can imagine if this part equal to m lambda, L2 minus L1 equal to m lambda, then all the light here, they will interfere constructively, so we have the maximum light. So this part equal to this one equal to the pitch sine beta, and the beta angle is the same as the theta angle, so equal to p sine theta equal to minus lambda. So here we said minus lambda, this corresponds to the minus 1 order. So you can imagine, we can define that to the left side we use the minus, and we go to the right side, to the right side we use a plus. And this is the first order. The second order will be the minus second order will be come to here. You can do the similar calculation. That's why I said that, optical part difference at any spot here, from here to here and from here to here, the optical part difference, there is the 2n pi here, n is the number of the greeting length, the number of the greeting length. But this 2n pi, come from here, come from this m lambda. So here the m, here you can imagine the m is the same as what I wrote n here. So this is something a little bit complicated, but I hope you can understand. So the key is that the wafer, the distance between the wafer and the grating, this distance should be far bigger than the size of the grating. So the distance here should be maybe 100 times the size of the grating. Then we will have this, what we want. We will have this formula. So here you can see the sin theta equal to lambda over p. Sin theta equal to lambda over p. The pitch on the grating is given by lambda 2 times sin theta, lambda over 2 times sin theta. Sin theta equal to lambda over p. So in the end, you get p over 2. So when there is some medium of n, then we get the number n here. So the conclusion is that the grating period on the wafer is always half that of the period on the face grating. So here you can see what is the magic. So if we use the mirror, when we use the mirror, so what's wrong with the mirror? So when you use the mirror, you can imagine this branch here comes to this spot. This branch, sorry, this one should draw the bottom one. This come here, the bottom one come to here, right? The bottom one come to here. So if the central beam has the same optical path difference, that means this one, the same optical path, then this part, the optical path difference will be very different from the central part. The optical path difference will be different from the central part. So when you do the assignment, questions, you can figure this out. That's why we cannot use mirrors. So we cannot use mirrors to guarantee we have the same optical path plus 2 pi times. But when we have the phase gratings, we can make sure the optical path difference is a number plus 2n pi. So here in this case, so we do not need a temporal coherence, but we still need a spatial coherence. So we still need a spatial coherence. That means this light here and this light here, this should be coherent. So how to relax the spatial coherence? So this can be done by using a two-phase grating. This phase grating 1, this phase grating 2. So they do not have to be the same period. The P1, P2. So they can be different. But here the drawing that shows the P1 and the P2 is the same. But when the P1 and the P2 is the same, the pitch on the wafer is given by, again, half of the grating period on the two phase gratings. So first, let's look at why we do not need spatial and temporal coherence. So we can see this branch here and this branch here. So they are symmetric. So the optical path difference is the same. So they will come here at the same time. So we do not need temporal coherence. So moreover, this X point corresponds come from here to here, corresponds to Y point. If we go to the right, also corresponds to the Y point. So the same Y point will give corresponding X point. So the light comes from the same spot. So obviously the same beam will interfere well with itself. That's why we do not need a spatial coherence. Actually, we also don't need to be monochromatic. That means there can be some bandwidth of the laser beam. It does not need to be the identical wavelength. That's why it is called achromatic. It's called achromatic. That means not monochromatic. So in this case, we use the 193 nanometer laser. This is the argon fluoride excimer laser. So we know that for the argon fluoride, for the excimer laser, it always pulsed. It is pulsed and it has poor coherence. So now we look at how to get even higher resolution. To get even higher resolution, we need to reduce the wavelength. So this is the case for the EUV near field lithography. So the EUV wavelength, it is 13.5 nanometer wavelength. This is the extreme UV. So we will talk about extreme UV lithography next week. So when we have shorter wavelengths, we get higher resolution of the gratings. But the requirement is that for this wavelength, for this short wavelength, so all the material will block the light. So we cannot use thick material. So we have to use a very thin membrane. So when we use very thin membrane, this light can pass through. Otherwise, this light will be blocked if we do not use very thin membrane. So the membrane here is on the order of only 100 nanometer. So the thickness for this membrane is 100 nanometer. So then again, the light comes from here. They go to one membrane phase grating, come here. The other phase grating come here. They meet to form the periodic pattern. So what is the period here? So the pitch here, as we said, the pitch here should be half of the pitch here. So that means if this one is 100 nanometer pitch, then this one will be 50 nanometer. Then you can use the 50 nanometer pitch to act to be used as another phase grating to get 25 nanometer. Then you can use 25 nanometer as the phase grating. You put this phase grating here. You put this fabricated grating as the phase grating. Then you get 12.5 nanometer pitch. So each time we have the pitch half of the phase grating pitch. So they can get 25 to 50 nanometer pitch. So the feature set can be very small. Exposure area can be very big. If you do the scanning the stage, you move the stage along the y direction, also move it along the x direction. So in the end, the big wafer can be exposed. So this work is only done by this group, Paul Scherrer Institute. So this is the Switzerland. So they have the synchrotron radiation to generate 13.5 nanometer wavelength. And also again, you can see here we have a pinhole, the same thing as we have seen before. This pinhole to make sure only the central beam passes through to guarantee a spatial coherence. Now here we look at how to make a higher resolution. We have 3 phase gratings. So this is, you put 2 of them, and you put 3 of them, you get a pattern, hexagonal array of the pattern. So now let's look at how to make large pattern area. So as we said, so the pattern area is limited by the coherent length and the vibration and other things of the optical system. So to have very high pattern area, we can use a very precise stage. This is called a interferometer stage. If this stage is very precise, we can first expose a small area. So you can consider we can first expose this area. So we have many lines. Expose this area. Then we move the stage. We expose another area. So if the overlap, if the alignment is much smaller, if the alignment is better than the grating period, then in the end we get long-range periodic pattern. So that means this stage here, the stage accuracy of this one should be much better than the pitch of the grating. So this stage has to be very precise movement so that the grating they can overlap without error. So you can have the in the end. So this group from MIT, they get a 30 centimeter large area grating, periodic grating with long range ordering. So they use this grating for the space application. So they use this one as the particle, like gamma ray and particles filter for the space application. The last topic is the immersion lithography. So we have seen that we can use immersion lithography to get better resolution for the case of the projection lithography. Can we do immersion for the near-field lithography? So you can imagine we have the light, we put the wafer in the liquid, but as you can guess, the resolution is not improved. because the pitch is given by lambda over n 2 senses. Lambda over n is the index over 2 senses, equal lambda over 2n senses. So we know that for the liquid, because of the Snell's law, so n1 Z1 equal to n2. So because of this Snell's law, so the unsensitive value here, this unsensitive value is the same in the liquid or in air. So in air, we do not get any smaller pitch. Then what we can do to improve to get smaller pitch using liquid? So what we can do this kind of setup. We can have the container, the liquid container like this. So the beam here is perpendicular. So here is also perpendicular to the surface. Then the light will pass through. They form the periodic pattern. They get higher period. Or we can use a glass. This one is solid glass, and we use some refractive index matching liquid in between. This should be better because this one there may be some vibration or bubbles in the beaker. But this one, everything is solid. We should have better results. So this is an example of the grating pattern with 180 nanometer pitch using 266 nanometer wavelength. So we know that half of lambda over 2 equal to 133 nanometer. So if we do not do inertial lithography, the maximum, so the smallest the period we can have is 133 nanometer. But here we get 118 nanometer pitch. Thank you.